Hello students, it's Mrs. Zimmers, and I'm making you a new video since most of my old videos are from a couple years ago and some of the lessons have been modified or updated. So I wanted to give you the fresh new lesson on inverse trig functions. And in class we start by doing this warm-up, and the warm-up was strategically written to help lead into today's lesson about inverse trig functions. So we're given that sine of alpha is square root 7 over 4. Alpha is not in quadrant 1. Cosine of beta is negative 2/3. Beta is not in quadrant 2. We use that information to make reference triangles for alpha and beta. So if the sine of alpha is positive, but it's not in quadrant 1, it must be in quadrant 2. And if the cosine of beta is negative, and it's not in quadrant 2, it must be in quadrant 3. Okay, so we draw the reference triangles and we use the Pythagorean theorem to find the missing side lengths. Once we have that information, we look to our identities, and for the sine of alpha plus beta, we know that it should be sine alpha cosine beta plus cosine alpha sine beta. We look to our reference triangles and we find all 4 of those exact values, and then we do a little bit of work with fractions to get our answer. It's not the most beautiful answer you've ever seen. And what I went ahead and did is put it in my calculator and got the approximate value. Okay, now let's see. Where did I put cosine down here? Yep, there it is. So then you look back at your cosine identity, your cosine sum identity. The cosine of alpha plus beta is cosine alpha times cosine beta minus sine alpha times sine beta. You look at your reference triangles, find all those values, plug them in, do your fraction work, and you end up with 6 plus square root 35 over 12. Also not the most beautiful answer ever. Put that in the calculator if you wish, and you get 0.993. Now, just a word of caution, when you're putting these in the calculator, be sure to have parentheses around the whole numerator before you divide by that denominator. Okay, then the third one we were asked to find is tangent. So the tangent of alpha plus beta is tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta. Look at the reference triangles, find all of those values, plug them in. From that point, to simplify, what I did was I noticed that the common denominator of all these would be 6, between 3 and 2, and 3 and 2 down here. So I multiplied the numerator by 6 and the denominator by 6 to clear the fractions, and I got this answer. And I did not go through the process of rationalizing the denominator, but I did find the decimal value of that. Now I was thinking, with answers this messy looking, wouldn't it be nice if we had a way to check these answers? So one idea is to remember that tangent is sine over cosine, and so if you took this fraction and divided it by that fraction, do you see how you would get this fraction? The 12s would end up canceling. When you, instead of dividing by the bottom, you would multiply by the reciprocal of the top. That would put a 12 on the top, and you have a 12 on the bottom, and the 12s would cancel. So that makes us feel good about this answer if the other 2 answers were right. How do we check those? So I was thinking, and some of you have suggested this in the past for a way to check the answers. What we could do is we could go back to this statement, sine of alpha is square root 7 over 4, and we could find the inverse sine with the calculator of square root 7 over 4, and that would give us the angle. Now it would be approximately something. And then we could do the same thing for this statement. We could go back and find the inverse cosine of negative 2/3, and that would approximately give us the angle. So that's what I'm showing you next. Okay, so what we have here for our check is the sine of alpha is square root 7 over 4, so alpha is approximately 41.4 degrees, and I went ahead and stored that in my calculator. Cosine beta is negative 2/3, so using inverse cosine, I got that beta is approximately 131.8 degrees, and I stored that in my calculator. And then I asked the calculator to find the sine of the sum of the two stored angles, and it gave me 0.118, and I looked back at the other computation, and that was the same. And then I asked my calculator to find the cosine of the sum of the two stored angles, and I got negative 0.993, and I looked back at my other approximate answer, and they were not the same. One was the opposite of the other. And then I did the same thing for tangent, and I took the tangent of the sum of my two stored angles, and I got negative 0.119, and that was not the same as the other one. So I'm a little bit worried. I don't know what's going on. I don't know if I made mistakes in my work before, or if the calculator's wrong, or what's going on. So let me tell you a little bit more about this. Here's what I want you to think about. You have infinitely many angles with the same sine value, infinitely many angles with the same cosine value, and so on. Here's a simple example. Let's just take the sine of 30. You get 1/2. But also, if you find the sine of 150, it's 1/2, and sine of 390 is 1/2, and sine of 510 is 1/2. And you can just keep adding 360, or you can just keep finding things that are coterminal with 30, coterminal with 150. And here's another example. The sine of 36,030 degrees is also 1/2. There are infinitely many of these. But your calculator can't give you infinitely many answers when you ask it to find the angle whose sine is 1/2. So in your calculator, when you type in inverse sine of 1/2, you're asking it for the angle whose sine is 1/2. Your calculator only knows how to give you one answer to that. And that should remind you of something. Think about functions. Functions have only one output for each input. So what your calculator understands is that inverse sine ought to be a function, and it should only give one output. So what we're going to do in this lesson is we are going to see, how does the calculator choose? What is the reasoning behind that one answer and not some other equivalent or some other answer with the same exact value, different angle? And there's one other thing that I left behind on the previous slide, so let's just take a look at that. Sometimes we're answering this question as well. Given that the sine and cosine and tangent of alpha plus beta are all positive, where, in which quadrant, would you find angle alpha plus beta? Well, if they're all positive, that would be, can you guess? You're correct, quadrant 1. Very good. All positive in quadrant 1. Don't forget, all students take calculus. All positive in quadrant 1. Okay, so let's move on to today's lesson. This is day 1 of inverse trig functions. And there will be things that I write that is just kind of development, background, reasoning, that I want you to watch and try to understand, but you don't have to write. And then we'll get to the part that you need to write. So don't write this first part. Something you already know. So this is from way back in chapter 4 when we looked at inverses. Inverses have x and y coordinates switched. Inverses are reflections across the line y equals x. And if you compose inverses with function composition, that is f of g, g of f, one inside the other, inverse operations cancel, leaving you with just x. Specifically about inverse trig, because those key points were about any kinds of inverses. Now narrowing in on inverse trig in particular, what you have done in the past is when you were trying to solve a right triangle, like number 10 here, I pulled this off of either a worksheet or a notes from notes earlier in the year when we started doing trig. We had this problem where we knew the opposite of angle theta and we knew the hypotenuse, but we didn't know the value of theta. So what we did was we set up the equation sine theta equals 6/9, and to undo sine and leave theta by itself, we took the inverse sine of both sides. Inverse sine of the left, inverse sine of the right, so sine and inverse sine canceled, and we just had theta equals inverse sine of 2/3. So look, When you're doing inverse sine, the input is a ratio, the output is the angle. Another example, number 11. So again, we had a right triangle. We didn't know angle theta, but we did know the opposite and we did know the adjacent. So we set up the equation tangent theta equals opposite over adjacent. And to isolate the theta, we took the inverse tangent of both sides. That way, inverse tangent cancels with tangent, leaving theta by itself. Theta is inverse tangent of 2. I just reduced the ratio of 12/6 to 2. And that gave us an approximate answer of 63.4 degrees. So once again, input the ratio, output the angle. Okay, so to summarize some of that, you can go ahead and write this down. With regular trig functions, you input the angle and you output the ratio. Sometimes we call that an exact value. So for example, for sine, the regular sine function, you could input 30 degrees and output 1/2 because the sine of 30 degrees is 1/2. However, for inverse trig functions, you're going to switch x and y, switch domain and range, input the ratio, output the angle. So if I switch the 30 degrees and the 1/2, inverse sine of 1/2 is 30. That means the angle whose sine is 1/2 is the angle 30 degrees. Okay, so here's the notation for the inverse sine function, y equals inverse sine of x. Sometimes it's written y equals arc sine of x. So you see the -1, that little notation means inverse, but it could be confused with an exponent. It's not an exponent. It's not the -1 power. This is not the 1 divided by sine of x function. So to clarify and avoid that confusion, you could write arc sine instead. Once again, don't write this first part. I want to show you where the inverse sine function comes from and what the function looks like as a graph. So you already know that the sine function looks kind of like this, right? Goes on and on and on and on. And its domain is all real numbers, and its range is -1 to 1. The y values, it goes up to 1 down to -1. So what if I wanted to take that graph and draw its inverse? What would the inverse of y equals sine of x look like? Well, I have to reflect this across y equals x. Okay, I apologize if I repeat myself, but I just had to pause for a few minutes and come back. So I believe what I was about to do is reflect this graph across the line y equals x, and we would get something that looks kind of like this. Which is cool. And to get the domain and range, we would switch the domain and range from the original, because the domain of one function is the range of its inverse and vice versa. The thing is, this is not a function. It does not pass the vertical line test, as you can see. And so for any particular input, let's just take this input right here, you would get multiple outputs. So that's the issue. So how do we avoid that issue? Well, what we do is we just use a piece of the sine graph. We restrict it to a smaller piece, a piece that would pass the vertical line test if you were to switch it around. And so for this particular graph, we take this little piece right here, and we reflect that across the line y equals x to get the inverse function. So what piece is that? Well, if you're working in radians, this x value is -pi/2, and this x value is pi/2. If you're working in degrees, that would be -90 degrees to 90 degrees. So here's the part I would like you to write. Here's what the graph of the inverse sine of x looks like. The graph of y equals inverse sine of x. I'm going to take that little orange piece that I just drew and reflect it across the line y equals x, and we get something kind of like this. Now, Looking back at the sine graph, if the x values went from negative pi over 2 to pi over 2, then that means for the inverse, the y values are going to go from negative pi over 2 to pi over 2. And, again, looking back at the sine graph, the y values went from negative 1 to 1. So looking at the inverse, the x values go from negative 1 to 1. So the domain of this little piece of a graph is negative 1 to 1, and the range is negative pi over 2 to pi over 2. That means when you input numbers into the inverse sine function, you have to input numbers that fall between negative 1 and 1, and when you output angles that fall between negative pi over 2 and pi over 2. Or, if you're in degrees instead of radians, negative 90 degrees to 90 degrees. So what you could do is grab your calculator, put it in degrees since that's what you're most used to, and plug in some numbers into the inverse sine function, like inverse sine of 0.9, inverse sine of 0.3, inverse sine of negative 0.2, as long as your numbers are between negative 1 and 1. You can do inverse sine of 1 and inverse sine of negative 1 as well. What you're going to notice is that your outputs are angles that fall between negative 90 degrees and 90 degrees. Well, if you think about where that is on a coordinate system, between 0 and 90 degrees is quadrant 1, and between 0 and negative 90 degrees is quadrant 4. So to sum it up, your answers, your outputs, are going to be answers from quadrants 1. I guess I don't have to put Q because I already have the word quadrant, don't I? Give answers from quadrants 1 and 4. All right, what we need to do is go through that same idea for inverse cosine and inverse tangent. So here is the equation, y equals inverse cosine of x, sometimes called y equals arc cosine of x. Here's the development. Don't worry about writing this part. Same idea. We have our cosine graph. Looks like this, right? Infinitely many of these things. Getting kind of sloppy. The domain is all real numbers, and the range is negative 1 to 1. If we were to reflect that across the line y equals x, we'd get this thing, which is not a function, would fail the vertical line test. So we don't want that. We want something that is a function. Now what I don't want to do is I don't want to take the same piece I used for inverse sine, which would go from here to here, because that translates into this, which is still not a function. So that's the wrong piece. So what else could I do? How about if I used this piece, which would correspond to this piece? That would be a function. So that's the piece we're going to use for our inverse cosine function. So you can write this part. The graph of inverse cosine, y equals inverse cosine of x, looks like this. Strange, eh? Now, what are the domain and range values? Let's see. If we go back to the cosine graph, this was 0, this was pi, if you're in radians, and height-wise, this was negative 1 and this was 1. So when we flip that around, the x values will be negative 1 to 1, and the y values will be 0 to pi. So domain, negative 1 to 1, range, 0 to pi. That's in radians, degrees, 0 to 180. Okay, so what does this mean for us in terms of like reference triangles and things? 0 to 90 is quadrant 1, 90 to 180 is quadrant 2. So, interpretation of range, when you're finding the outputs for your inverse cosine, always give answers from quadrants 1 and 2. Now let's look at something. For the inverse sine function, we gave answers from quadrants 1 and 4. Sine is positive in quadrant 1, negative in quadrant 4. For the inverse cosine function, we give answers from quadrants 1 and 2. Cosine is positive in quadrant 1, and negative in quadrant 2. So you're always going to have two quadrants, one quadrant where it's positive, one quadrant where it's negative, and just to keep it simple, we'll let quadrant 1 always be the quadrant we use for the positive. Then it will either be quadrant 4 or quadrant 2 for the negative. It just depends on the function. Okay, so let's do the same thing for inverse tangent, sometimes called arctangent. Don't write the first part. Developing the idea. Remember the graph of y equals tangent of x. You've got things that look like this, infinitely many of them, so on and so forth. Well, if I was to take that and reflect it across the line y equals x, I would get something kind of like that, with another one, and infinitely many of those, and that's not a function. Now the original one, if we were to write the domain, it's a little bit trickier because it has asymptotes at pi over 2, negative pi over 2, etc. And everywhere it has an asymptote, that number is not in the domain, and so that's going to be a little bit tricky to write. I'm just going to leave that for now. The range, all real numbers. So for the inverse tan, the domain would be all real numbers. The range, let's figure that out in a moment. Let's figure that out after we have restricted it to just a certain piece. So it would make sense to me just to take this middle piece, reflect that across the line y equals x, and we get just this piece, and that piece is 1 to 1. It passes the vertical line test, passes the horizontal line test, it gives us a function. So here's what you can write. The graph of y equals inverse tangent of x looks like this, where the domain is all real numbers. And what about the range? Well, if we go back, remember the original tangent graph, that one piece went from negative pi over 2 to positive pi over 2. So looking at the inverse, those heights would be pi over 2 and negative pi over 2. The thing is, it doesn't actually reach those heights because of the asymptotes. So when we write the range, we're going to write open brackets, not closed, open brackets, negative pi over 2 to pi over 2, or if you're in degrees, negative 90 degrees to 90 degrees. This is going to be a little bit different for you to give an answer that's a negative degree answer as opposed to giving an answer of like 300 degrees, which you're used to for quadrant 4. Instead, you would say negative 60. So once again, 0 to 90 is quadrant 1. 0 to negative 90 is quadrant 4. Give your answer as a negative number so it falls within this range, as opposed to giving your answer as a positive number that's 300 or 360 or whatever it is. Those are from quadrants 1 and 4. Okay, that takes us through the concepts. Next, what we're going to do is summarize. Okay, so the orange piece, orange, red, whatever color that is, that represents the graph of the original trig function, not the inverse trig function. Just so you know, this is sine, cosine, and tangent, but what this picture is showing us is just the piece we took and modified. What I wanted to say is that you can do the same thing for secant, cosecant, and cotangent and find graphs for inverse secant, inverse cosecant, and inverse cotangent. Here are the regular cosecant, secant, and cotangent graphs. You would take the red piece and reflect it across the line y equals x, and that would give you the inverse. We're not going to focus on those. We're just going to focus on sine, cosine, tangent. So you're not responsible for that. I just wanted you to know that they exist. Next, we're going to work through some examples. So, number 1 says find y in each equation, and in your book it's going to look like this as well, and they're going to ask you to find the answer in radians, and then in a future problem they're going to say find theta in each equation and ask you to find the degree measure. Well, I've decided let's just do both, so I've written these instructions, answer in degrees and radians. Okay, y equals arc sine of square root 3 over 2. That means find the angle whose sine is square root 3 over 2. So the first thing you acknowledge is that that is a positive number, and sine is positive in quadrant 1. So draw your reference triangle in quadrant 1. Sine is opposite over hypotenuse. Hopefully you recognize that triangle. Put a 1 on the other side. And hopefully you recognize that angle is 60 degrees. So y is 60 degrees. Or, convert it to radians, y is pi over 3 radians. Okay, part B. Find the angle whose sine is negative 1/2. Notice it's negative. Sine is negative in quadrant 4. So draw your reference triangle in quadrant 4. See, reference triangles, they just never go away. Negative 1 on the opposite, 2 on the hypotenuse. Hopefully you recognize that triangle as well. Square root 3 on the adjacent, and that would be a 30-degree angle. You're used to saying that you have 330 degrees, and I understand that because usually we go counterclockwise. But remember, we're supposed to give answers for this function between negative 90 degrees and 90 degrees. So we're going to say negative 30 degrees. And in radians, we're going to say negative pi over 6 radians. Okay, let's do the next one. Y equals inverse sine of square root 2. So find the angle whose sine, sorry these are all sine, but you would do the same thing with tangent, cosine. For some reason, these all turned out to be sine. And whenever you don't have a ratio, just put it over 1 to make a ratio. Okay, notice that that is positive, and sine is positive in quadrant 1. So draw the reference triangle. So we would put square root 2 on the opposite and 1 on the hypotenuse. At some point along the way, you should realize that there is something wrong. Square root 2 is greater than 1, and there's no way to have the opposite greater than the hypotenuse. And if you think about it another way, your sine graph, your normal sine graph, only goes up as high as 1. It doesn't go up to a height of square root 2, so there's no way to find an angle that had a sine value of square root 2. So this has no solution. We can also tie this into what we said earlier, that the domain of the inverse sine graph has to be from negative 1 to 1, and square root 2 is outside that domain. Are you noticing the lag in my computer at this point? I think it's getting tired, just like we are. But we are getting close to the end of this lesson. We have number 2 and number 3. And that'll be it. So for number 2, we're going to use inverse or arc cosine. Remember, they mean the same thing. The angle whose cosine is 0. Oh, when you get a 0, you have to switch gears. And instead of thinking about reference triangles, you can think about the unit circle. The angle whose cosine is 0, well, let's see. Here's the point for 0 degrees. Here's the point for 90 degrees. Here's the point for 180. Here's the point for 270. Where is cosine equal to 0? At 90 and at 270. But what was the accepted range of outputs for this function? Outputs need to be between 0 and 180 degrees, quadrants 1 and 2. So we're going to give the answer of 90 degrees. And then converting that to radians, pi over 2 radians. Okay, part B, y equals inverse cosine of 1/2. Notice that 1/2 is positive, and so we're going to be in quadrant 1. Draw a reference triangle, put 1 on the adjacent, 2 on the hypotenuse, and you have square root 3. Recognize that triangle, 60-degree reference angle, so y is 60 degrees, or in radians, pi over 3. Hopefully it's starting to just click for you the more we do. All right, let's do one more. This one says just find degree. I suppose we could do it in radians and degrees if we want to. So find the angle whose tangent is square root 3. We can make that a ratio. Oops. Square root 3 over 1. It's positive, so we're in quadrant 1. Draw the reference triangle. Arctangent, so tangent, it would be square root 3 over 1. Recognize that one. See, we keep going back to the ones we know. 60 degrees again. So theta is 60 degrees, or if you want to put it in radians, pi over 3. Okay, next time we'll do inverse trig day 2, and we'll get to some more complicated problems. I'm sure you're excited about that. For now, thank you for watching, and this is our assignment.